It is my great pleasure to introduce our speaker today, Professor Dan Purovich. Dan is a professor at the Thayer School of Engineering, Dartmouth College. He received his Bachelor of Science in Physics from Michigan State University and then Master and a PhD from University of Washington. He is elected as Fellow of the AGU in 2013 and has won several awards and medals, including the National Science Foundation Arctic Service Award in 1999. Dan has served on numerous steering committees and panels. His research is focused on the geophysics of sea ice, with particular emphasis on electromagnetic, thermodynamic, and morphological properties. A central element of his work is observing and understanding the role of the sea ice albedo feedback in the Arctic climate system. It is exciting that the international MOSAiC expedition with the German research icebreaker Polarstern will launch in autumn 2019. This could be the largest-scale Arctic research expedition of all time. As a member of the project board, Dan will tell us more about the MOSAiC. Now, let's turn the screen to Dan, and thank you.
Thank you. The evidence is unequivocal. The Earth is warming. We can see it in this plot here that shows changing temperatures over the past 50 years with time as the x-axis and latitude as the y-axis. And we see in the past few decades it's been warming pretty much everywhere. And what really gets our attention is what's happening in the Arctic. Here we see the greatest warming as much as 2 to 3 degrees centigrade. And we can look ahead into the future and see what models are projecting for future changes. This plot shows changes in temperature, surface temperature from the beginning of this century to the end of the century. And there's two key elements in this plot. One, once again, the Arctic is where we expect there to be the greatest warming. And two, it's also the area of the largest uncertainty in climate projections. I mean, this really gets our attention. We see that there's the potential for large warming, but still uncertainty, implying some things that we need to understand better. And we can look at one element of the Arctic system, and that's the sea ice cover. You know, here we see a familiar plot showing observations and model projections for sea ice over a couple of centuries, and we see the observations in orange are lower than what the models are projecting. And so when we put this all together, we have an area where there's large changes expected, things that we're not quite understanding, and the expectation is that there's processes in the Arctic climate system that aren't being correctly represented in the large-scale models. If this wasn't complicated enough, we have an Arctic sea ice cover that's undergoing tremendous changes. We can see that there's been a retreat in the ice extent in all months, particularly at the end of summer. We see that there's been a fundamental shift in the ice cover from being predominantly multi-year ice to being predominantly first-year ice. And we see that in general, the ice cover has gotten thinner. So we have a changing Arctic sea ice cover in an Arctic where we've seen that there's large warming. And we expect there to be even greater warming in the future, though there's still quite a bit of uncertainty about that. Combining that all together is the motivation for MOSAiC. MOSAiC is the Multidisciplinary Drifting Observatory for the study of Arctic climate. MOSAiC is big, interdisciplinary, and international. It's international with more than 17 countries participating, with the centerpiece of the German icebreaker Polarstern. It's interdisciplinary because we're bringing together researchers from the atmosphere, sea ice, the ocean, biogeochemistry, and ecosystems. And it's large. There's literally hundreds of researchers currently participating in MOSAiC. So what MOSAiC, its central goal is to improve the understanding of coupled atmosphere, ice, ocean ecosystem processes in the Central Arctic to support improved sea ice forecasting, regional weather forecasting, and climate predictions. Basically, MOSAiC is looking at the system to try to understand the processes driving the system so we can use that understanding to improve models. There's a recognition that reliable climate predictions are needed now. MOSAiC is designed to integrate between disciplines and also to integrate between observations and modeling. One of the features of MOSAiC is it's an experiment where modeling is an integral part of the planning of MOSAiC from the very beginning. The hope is that MOSAiC will lead to breakthroughs in Arctic climate science, and it's really a unique opportunity. A chance for a year-long drift experiment is something that really comes along once in a career, or maybe if you're really lucky, twice in a career. And I can think of nothing that would be more exciting to be an early career scientist participating in MOSAiC. And it's slated to be the largest Arctic research expedition ever. MOSAiC is big. In addition to the goal of MOSAiC, it has science questions. The overarching science question is, what are the causes and consequences of an evolving and diminished Arctic sea ice cover? There's also 5 questions supporting that. There are questions regarding the heat and momentum balance budgets of sea ice. There's also a question looking at how does sea ice move? How does it deform over its first year of existence? There's also a lot of interest in looking at understanding what the formation and the properties of Arctic clouds and how are they interacting with aerosols in the boundary layer structure. There's also an interest in ecosystems and the major elemental cycles in high Arctic sea ice. And then also there's a question regarding how do these ongoing changes in the Arctic ice-ocean atmosphere system impact the large-scale heat and mass balance transfers in terms of climate and ecosystems. Those are the overarching science questions of MOSAiC. And that leads to main science focus areas and some of the design of the experiment. Again, MOSAiC is highly integrated, highly interdisciplinary, and we're looking at it as a system. We'll be looking at sea ice, first of all in terms of how it moves, how it grows, how it melts, but also its connections, how it's coupled to the atmosphere, what are the energy and momentum fluxes. What's the impact of clouds and solar radiation and long-wave radiation? What are the biogeochemical fluxes from the ocean to the atmosphere? And what's going on in terms of ecosystems? So we're looking at these major science focus areas from a system approach. The general research approach is to have models informing observations to improve parameterizations for better models. And you'll hear me say that a few times through this talk. And it starts out with a field experiment, a set of year-round observations in the central Arctic. Observations that will be used in the development and improvement of process models to look at the processes in Arctic subsystems, and then to take that information to develop and improve the parameterizations both for weather prediction models and climate models. The observations will be assimilated into numerical weather prediction systems. That information and also the climate information will be sent off to services for stakeholders in society. We realize in MOSAiC it's not just an intellectual exercise. The work of MOSAiC is really designed to help our ability to understand what's going on to the Arctic and improve our ability to predict what's going to happen to serve society and stakeholders. The general structure of MOSAiC is based on working groups. There's 5 working groups: the atmosphere, sea ice, ocean, ecosystems, and biogeochemistry. Even though we have those 5 specific working groups, we've designed things so that they're not in their own bubble, that there's strong interactions between groups. And one of the ways those groups are brought together is through modeling. Modeling reaches across all of MOSAiC. And there's also, in addition to modeling, there's cross-cutting working groups. There's elements of MOSAiC that will be impacting some or all of these working groups in terms of aircraft operations, remote sensing, communications and outreach, data science, and logistics. So MOSAiC is an interdisciplinary study that has these 5 working groups. If we look at the overall general approach, It's a drift experiment. There's a central observatory, the polar stern, which will be frozen into the ice and allowed to drift from September 2019 to September 2020. Around that central observatory, there will be a distributed network with stations with autonomous instruments that will be visited periodically. Also, to extend the geographical coverage, there will be operations with helicopters and aircraft, and also satellite data. And as we'll see, there'll be visits to MOSAiC by icebreakers and other MOSAiC partners. So if you're going to have a drift experiment, the question is where? MOSAiC will be following along the general drift of the Fram. We'll be drifting along in that area. To remember, the Fram took 3 years. We're looking at MOSAiC as being 1 year. And the drift is really an important component of it, and there's already been a number of model simulations looking at different starting points and see where the drift of MOSAiC would take us. And to do that, a major part of a year-long drift experiment is picking a flow. And when we're trying to pick a flow, there's really 2 components to that. There's what kind of flow are you looking for, and where do you want the flow to be. In terms of the optimal flow, we want to have the base of operations a flow that's at least a second-year flow, that's over 1 kilometer in diameter, and has a thickness greater than 1.5 meters. But we also want this flow to either be in the marginal ice zone or close to the marginal ice zone, because we want there to be new ice and open water nearby the flow. Because again, MOSAiC is designed to look at the new Arctic that's dominated by first-year ice. Where do we want it to be? Well, we want to start in the lap test C, but we want to stay out of the Russian EEZ. And we want to come out of the Fram Strait, and we want to do it not too early, but not too late. And as you can see, there's been a lot of work done by Thomas Crumpton looking at different scenarios, different starting points, running forcing data from different years, and coming up with probabilities of different outcomes. And we're using that to kind of guide where we think we'll be starting from, but of course the exact location will depend on the conditions that we find, the ice conditions we find a year from now. Now, it's a year-long drift experiment, but nobody's really planning on being there for the full year, and also the polar stern will need to be resupplied in terms of fuel and in terms of food. And because of that, the year-long drift is divided up into 6 legs. You can see that across the top of this slide. The legs typically are 2 months long. The first leg is a little bit longer, it's 3 months, and the last leg is a little bit shorter, it's 1.5 months. And below that timeline, you see the 4 icebreakers that will be coming up to assist the polar stern during this drift experiment. The academic Fedorov will be coming up in the initial deployment to help out with the deployment of some of the satellite instrumentation. Now, these cruises, these supply cruises, are also an opportunity to do some science. And indeed, we're planning to do science on these cruises because it's a way to extend over space the observations. There won't be a possibility for there to be extra scientists on board, but there will be scientists on the way up that are going to the polar stern and on the way back going home. And the science by those groups are really encouraged, and we're developing various sampling plans to look at ice conditions, the atmosphere, and the ocean. Now, MOSAiC, the observation strategy, is based on a nested multiscale observations with 3 scales: the central observatory, the distributed network, and large-scale linkages. The central observatory is ship-based. It's around the ship on a scale of roughly 5 kilometers. The way I think about it, it's a scale where you can go and walk out to make your measurements. There's also a distributed network that goes on the scale of around 50 kilometers that'll have autonomous instruments, may have AUVs and UAVs, and it's designed to try to give us information on a model grid cell. And then there's large-scale linkages, where we'll be able to get information from the resupply cruises, from aircraft and some satellites to provide us information that will be useful for data assimilation studies and Arctic regional and global models. So let's take a look at those different scales. We'll start off with the Central Observatory. It's a 5-kilometer scale. And what we're trying to do here is to get a complete set of integrated measurements. We want to imagine a column that goes from the top of the atmosphere, through the ice, into the ocean. We want to know everything about that column in terms of atmospheric properties, ice properties, ocean properties, ecosystem studies, and biogeochemistry. And what you see here is a map, a potential map for the deployment. You'll see there's an area in the middle, which is the thick flow that we hope to find and dock to. Down on the lower part is the thinner ice, where we'll be studying first-year ice. And you can see there are places identified where we'll have a central area for the ocean measurements and for the Met measurements, Ocean City and Met City. There's areas for ice coring and snow sampling. And there's also, as we go further afield, no-go areas that you can think of as wilderness areas where we really want to limit the amount of activity there to keep them as pristine as possible. Now, of course, this will change when we get and find the flow we're on, but it's really important in the planning stage. You find an ice flow and it seems so big, but when you spend a year on the ice, you can use that ice flow up pretty quickly. So it's important that we have a plan for who's going to be where on the ice during these measurements. Going up the scale to the distributed network, it's mainly a bunch of autonomous buoys. You see in the figure the PS in the middle, that's the polar stern. There's 4 circles with S's and S pluses. Those are the super sites. They're in essence mini mosaics that basically there'll be autonomous instrumentation there to look at what's going on in the atmosphere, the ice, and the ocean, and also make biogeochemical and ecological measurements as well. In addition to those measurements, there'll be a lot of position buoys. The number keeps increasing as more and more people get involved, but the last I heard, there'll be roughly 50 GPS buoys placed in an array around the ship, looking at nested arrays at different scales to really look very closely at ice deformation. There'll also be measurements of ice stress, ice mass balance, snow depth, surface conditions. We'll have full measurements of radiation, wind speed and direction, barometric pressure and humidity. There'll also be some instruments looking at wave interaction and other things as well. So this is an idea to help us scale up what's going on in the Central Observatory and give us a good sense of what's going on the scale of a grid cell. And then there's the large scale. The large scale will mainly come from autonomous sites, autonomous vehicles, ships, aircraft, and satellites. This will come from information observed during the resupply voyages. There's also intensive aircraft periods where there'll be a number of overflights, not just of the camp, but in the region around the camp. And there's also an extensive remote sensing program for MOSAiC. And remote sensing from a couple of perspectives. One, a lot of satellite resources will be focused on MOSAiC, the immediate MOSAiC area and the broader picture as well. But there'll also be remote sensing work done on the polar stern. There's plans for some ground truth observations to help improve the algorithms that are used in remote sensing data to go from the electromagnetic signal to a geophysical parameter. Now, just as we have nested scales for the observation program, there are also nested scales for the modeling. On a small scale, the goal is to get a process understanding. This will be done through large eddy simulations. With that process understanding, it will be scaled up into a single column model used in terms of validation and also evaluation of various processes. And then the results of that will go into a regional system for a regional climate model, and eventually go up into an Earth system model. So the idea from the modeling is to go from small-scale processes all the way up to Earth system modeling. And I want to mention that MOSAiC has a very strong connection to YOP. In fact, YOP has added a special observing period for MOSAiC. It will be in the winter from the 1st of February to the 31st of March in 2020, and during that time there will be roughly 2,000 extra radiosondes that will be deployed from Arctic stations in support of MOSAiC. MOSAiC is considered by YOP to be a drifting supersite, and from the very beginning of MOSAiC there's been discussions with YOP, and there's data sharing between YOP and MOSAiC. So let's take a look now at some of the observations that are going to be made. And I think when you hear these observations, it's really very impressive how much work is going to be going on. And what I want to emphasize is it's impressive, for example, what observations are going to be made in any element. But in my mind, what's really impressive are two things. One, these observations will be made for a full year. And two, the real power of these observations is when they're combined, when they're fully integrated to take a systems approach. In terms of the atmosphere, we'll be looking at the atmospheric boundary layer and the structure of the atmosphere. There'll be 4 times a day radiosondes. There'll also be a med tower, 20-meter med tower. They'll be looking at profiles of the boundary layer. There'll be Doppler lidars and sodars looking at what's going on in atmospheric dynamics. There'll be a lot of work done on clouds. They're recognized as the key element. There'll be radar measurements and lidar measurements. And one of the things that's really exciting about MOSAiC is there'll be extensive aerosol work. Air sampling of cloud condensation nuclei and the composition of those. And I think that's something that's really an addition to MOSAiC that's been missing in some of the past work. Also, in terms of the atmosphere, there will be an extensive study of the surface energy budget in terms of radiation fluxes, turbulent fluxes. This will be done at the central camp and also at remote stations. And one of the things that we want to be in MOSAiC is flexible. We want to be opportunistic and look at opportunities. And one of the things in particular are leads. If a lead opens up, we're going to go and we're going to look at that lead from all elements, atmosphere, ice, and ocean. Also supporting the atmosphere, there'll be aircraft campaigns looking at clouds and radiation. And again, there'll be work in the atmosphere for large-scale linkages with land stations and other collaborating research vessels. In terms of the ocean, there'll be a focus on the ocean structure, the heat content of the ocean, salinity, freshwater input. There'll be periodic deep ocean profiles, and there'll be frequent upper ocean CTD profiling. Also, there'll be an extensive look at the flux of heat from the ocean to the ice through flux buoys. There'll be current profilers, a turbulent mass to look at the ocean boundary layer, and there'll also be transects with gliders. And again, we're going to be opportunistic. If a lead opens up, we're going to go and take a good look at it. Or for that matter, if a ridge forms, or if there's any impressive event that occurs during MOSAiC, we're going to have an intensive period to examine that. There's also biogeochemistry. People will be looking at carbon, CO2, methane, carbon monoxide, at sulfur, at nitrogen. There'll be sampling of the air, the snow, the ice, and the ocean. There'll be trace gas analysis, and they'll also be looking at photochemistry in the halogen and mercury cycles. There'll also be ecosystem work. There'll be profiling on ocean sampling and ice sampling of oxygen, chlorophyll A, nutrients. They'll be looking at primary production in terms of carbon and nitrogen uptake and oxygen release, and also looking at particle fluxes. And opportunistic, again, sampling at leads, making intensive measurements during the spring bloom. Now, since this is a talk for the Sea Ice Prediction Network, And since I'm a sea ice geophysicist, I thought I'd take a little bit deeper look at what's going on in terms of sea ice. It's an incredible opportunity to take a new look at a new Arctic sea ice cover. And one of the things with the sea ice group, we realize that sea ice is a central component of the system, and we have to work to have strong connections within our group and also between groups. For example, sea ice is connected to the atmosphere because sea ice is the great integrator of heat. It's connected to the ocean because during winter it's a source of salt, and during summer it's a source of fresh water. It's connected to biogeochemistry because the ice cover is an impediment to exchange between the ocean and the atmosphere. And it's connected to ecosystems because the ice cover is a moderator of sunlight. In terms of sea ice, we're going to be looking at snow, the ice, dynamics, sunlight, and mass balance. And we have, in addition to the overall MOSAiC questions, there's also some sea ice questions. What are the connections between dynamics and thermodynamics? What are the relative contributions of different processes to ice loss? How can we define the heterogeneity of the snow cover and the ice cover? And what are the balances? What are the balances of heat, mass, and fresh water? And what are the new properties, processes, and parameterizations that we have to consider in the new Arctic in terms of the snow cover, in terms of ice dynamics, in terms of the ice albedo feedback? And most importantly, how does first-year ice behave in the system? The key sea ice observations fall into broad categories of dynamics, thermodynamics, heterogeneity, balances, and evolution. We want to know about ice dynamics and thermodynamics. Those are the two processes that govern the ice cover. We want to try to explain the tremendous heterogeneity we see in the ice cover and be able to do balances of heat and mass, water, snow, and sunlight. And of course, the ice cover is always changing, and we have to be able to understand the evolution of the ice cover. So let's take a look at some of the sub-elements of the sea ice studies. There's snow morphology. We're interested in snow depth. What's the spatial variability of snow depth? What's the temporal evolution? We'll be doing lots of surveys of snow depth, both at points and also spatial surveys covering areas looking at snow depth. We're interested in thermal properties. We'll be doing temperature profiles in the snow and also doing a lot of work examining what is the thermal conductivity of snow, how does it change. There'll be a number of snow pits done looking at the stratigraphy of the snow cover. What's the grain size? What type of snow do we have? What's the specific surface area? What's the density and the water equivalent? What are the level of contaminants? For the snow, it's what is the spatial distribution and temporal evolution of the snow cover. For the ice physical properties, we'll be taking ice cores. One of the things that I find really exciting about MOSAiC, it's a mix of the old and the new. Some of the techniques we will be using have been used forever, like ice coring, and some of them are new. With these ice cores for MOSAiC, we'll be able to analyze the ice cores in an onboard CT scanner to get a full three-dimensional picture of the ice microstructure that will allow us to look at ice porosity, permeability, and conductivity, and inclusion size distributions. And from the basic cores, we'll look at ice structure, profiles of salinity, temperature, brine volume, and we'll also take oxygen isotopes. And there's also large-scale ice morphology. Generally speaking, we want to look at the surface roughness and the surface topography, the ice thickness, and the flow size. For the ice thickness, it'll be everything from drilling holes through the ice to using electromagnetic induction sensors to using terrestrial lidars. And we also want to look in detail at some of the features that the ice cover has. In the summer, it's melt ponds. What are the size of the ponds? What area fraction do they have? What's their shape? What are the depths of the ponds and the temperature and salinity in the ponds? And what are there false bottoms beneath the ponds? There's also ridges. What's the sail and the keel size of ridges? How do they form and how do they evolve? How does a first-year ridge consolidate, and what are the melt rates in that ridge? And then there's also leads. Leads are always interesting. In winter, leads are areas where there's tremendous fluxes of heat from the ocean to the atmosphere. In the summer, the roles are reversed, and the leads absorb 90% of the incident shortwave radiation, heating up and causing melting. We want to be looking at topography, ponds, ridges, and leads. We also want to look at the ice mass balance, just that simple concept of how much does the ice grow in the winter and how much does it melt in the summer. How much does it melt on the surface of the ice, the bottom of the ice, in the interior of the ice, and on the edges of the ice. To do this, once again, we'll be using some old technology, ablation stakes and thickness gauges, where we hope to measure the mass balance at every kind of ice we can find at many, many sites, between 50 and 100 sites. And we'll also be able to use it, make these ice mass balance measurements using new technology and autonomous instrumentation. And we want to look around at the edges of flows so we can see what happens to that heat in the ocean. How much of it goes to melting on the lateral edges of flows, how much goes to melting on the bottom of the flows. And there's also solar partitioning. It's really a simple question. Where does all the sunshine go? Simple question to ask, a difficult question to answer. And to do that, we want to measure the optical properties of all ice types over space and time. This will be a combination of optical measurements and physical characterization. Optically, we'll be measuring spectral albedos at points and along transects. We'll be looking at the spectral transmission and also looking at profiles of light in the upper ocean. And these optical measurements will be supported by physical measurements of snow depth, ice thickness, ice properties, the stage of melt, pond fraction, the presence of algae and particulates in the water. And with this combined data set, we can develop rate of transfer models and parameterizations that will enable us to model where does all the sunshine go. And our goal here is improved simulations of the ice albedo feedback. There's also ice dynamics. One of the keys is to try to relate dynamics and thermodynamics. How does the ice dynamics in winter impact the thermodynamics of summer? To look at ice dynamics, there'll be a major effort measuring ice thickness. There'll be work to try to determine what's the appropriate rheology to use when looking at ice dynamics. And a major effort trying to identify the scaling properties of deformation. And this will entail an array of stress sensors around the ship, use of the ship's radar to see what's happening on a close scale, high-resolution LiDAR around the ship, and that network of GPS buoys I talked about earlier, and also satellite imagery, in particular SAR imagery of the area around MOSAiC. The key is, how does first-year ice move into form? Now, if that all wasn't enough, we also plan to have intensive observation periods. These are periods where we're going to focus intensely on particular events. For example, winter dynamics. We expect that during the course of the winter, there'll be periods where the pack will become very active, forming ridges, opening up leads, and we're going to really focus on those periods and be prepared to spend an amount of time to look at that. In the spring, we're planning on working with the ecosystem group to look at the spring bloom, to see the relationship between changing ice conditions, changing sunlight, and primary productivity. In summer, we expect there to be periods where there's intensive melting, and we want to understand what's going on there. We want to understand the evolution of ponds and how the bright ice breaks up in summer. And then in fall freeze-up, a big question has to do with the loss of heat in the ocean. So what we'll be doing in these intensive observation periods is focusing on the critical periods and processes for sea ice. Now, that may seem like a lot to do, and given that there's 6 different legs, we don't expect anybody to be there the whole time. This calls for a lot of planning. And each group is coming up with a 2-week schedule and a schedule for every leg that tries to give a first-order estimate of what people are going to be doing. And here you see such a schedule for the sea ice group. It assumes there's 8 people. There's a schedule for the morning, a schedule for the afternoon, who's going to do what, looking at ridges or ROV work. You'll see there's green areas of flex time. That's when you'll be able to go off and kind of do your own thing, because one of the things that we realize for MOSAiC is that we need to define a set of core measurements that the entire group is committed to making happen. And then in addition to those core measurements, there'll also be measurements of particular interest to an individual research or research team. But these schedules are designed to represent what the group is committed to doing. Now, in addition to the observations, there's also going to be a large modeling effort. For the sea ice group, the modeling effort has a number of elements. There's a hope to make valuable contributions to the sea ice outlook. There's a plan to use MOSAiC observations to improve data assimilation into models. There's a plan to apply complex thermodynamic sea ice model into including biogeochemistry, and then to improve parameterizations and mixed layer processes into a 3D model, and finally take all this and use it to improve coupled climate models. And I want to just go through one example to give an idea of how this modeling will work and how it will be connected to observations. And to do that, I want to look at one example where we're trying to work on improving the treatment of the ice albedo feedback. Now, the first step is we started off with the community or system model, and we've run some sensitivity, and this is work that's happening now. We've done some sensitivity studies to try to get a sense of what factors may be impacting the ice albedo feedback. We've taken that information and then gone to a single column model to look at things in more detail. The single column model has the advantage that it's computationally much simpler, which means we can do more runs. So we're exploring the impact of different parameters like how snow is distributed, what's the ice thickness, what's the pond fraction, how are the ponds distributed, to look at the impact of those things on albedo. And then, based on that, we're designing an observation plan. We're designing an observation plan for the fieldwork on MOSAiC that will best address what the model considers to be the key parameters. It will help us decide how often to make measurements, over what spatial scales to make measurements. And really, we're using the model to help us design the observational program. When MOSAiC is over, we'll take those observations, sit down and work on parameterization development, try to use those observations to improve the parameterizations, and then finally feed those new parameterizations back into the large-scale community or system model. And we think that this is really a very nice positive feedback cycle. And I think it's representative of what's going on across the various disciplines of MOSAiC, this close connection between modeling and observations. And with MOSAiC, data is the key. The data are the legacy. And because of that, MOSAiC has a very strong commitment to data sharing and data archiving. The idea is to promote data fairness, promote data accessibility, with a major focus on observation to archive. MOSAiC is developing an automated data flow, which will include data scientists on board the Polar Stern to help facilitate this. There'll be data processing and storage on board the Polar Stern. The overall goal is a complete data set that's published with full metadata, that's archived in Pangea, and that each of the data sets in this large data set will have a DOI. So there's a very strong commitment to data sharing and archiving. Finally, MOSAiC is just a tremendous opportunity. You really don't have many chances to spend a year on the ice, to look at the full annual cycle, to do it in an interdisciplinary project where you're looking at the atmosphere, the ice, the ocean, biogeochemistry, and ecosystem, to examine a wide range of spatial scales, and to look at the new Arctic and examine first-year ice, to perform process studies, and to use that information to improve models. This is just a great chance to improve our understanding of the new Arctic, and it's just incredibly exciting. So, MOSAiC, do you want to know more? Of course you want to know more. You can check out the MOSAiC webpage. You can also contact me. I'm always delighted to talk about MOSAiC. And with that, I'll be glad to answer questions.
Thank you, Don. That was a great presentation, and we do have several questions. I'll go ahead and read them from the chat panel and then let you answer them. The first one is from Ben Holt, and he asks, will there be a detailed measurement of the surface roughness of the bottom of the sea ice cover?
There's plans to do that. There'll be very detailed measurements of surface roughness. That's all locked in with terrestrial LiDARs. In terms of the bottom roughness, that's been identified as a really important topic, and it's some of the details are still being worked out, but it'll probably involve ROVs and AUVs.
Thank you. The next question is from Christian Sampson, and the question is, will there be any time series LiDAR measurements of pond formation?
Yes, absolutely. The plan is to set up an area towards the wilderness area, if you remember that plot, and make LiDAR measurements through the whole year. And so I think the idea is to see how the surface topography changes, how the snow cover changes, relate that to where the ponds form, and then how the ponds evolve. In fact, there's going to be a little course this spring on how to use a LiDAR so that we make sure that there's somebody on board each leg that can operate the LiDAR.
Thank you. William Manley asks, or says, what a tremendous opportunity for disciplinary science. And the question is, will the location and tracks of the polar stern, buoys, and other observing sites be shared in near real time via text files, shape files, or in a web service, etc.?
Certainly the position will be available in real time. One of the things that we're still working on is how much bandwidth we're going to have in terms of sending data back, and I think the hope is to make as much data available as possible in real time.
Thank you. And as a follow-up, I think Haley Shen asks, when will the data be available? Is there a need?
Yeah,
want to add to that?
The data policy hasn't been finalized yet. Just in terms of things coming up, the next big MOSAiC meeting will be this coming March. There's a data advisory group that's been set up. In the implementation plan, they talk about a preliminary plan for data, and I think some data will be made available, or at least preliminary data will be made available in real time. Complete data sets should be done a year or two after the experiment.
Thank you. And Evelyn asks, will the ocean measurements be able to provide measured boundary conditions / advection tendencies for a single column modeling?
I think that's the plan. I'm not totally certain about the ocean component, but I'm pretty sure that's their plan.
Thanks. Harry Stern asks, how is MOSAiC different from Sheba in 1997 through 98?
Well, I have to say, Shiba's my all-time favorite experiment, but MOSAiC has the potential to do even more. I think there's a few ways that it's different. The most basic way is that it's a new Arctic Ocean. We have an Arctic Ocean where first-year ice dominates, and if you look at the earlier studies, you know, Shiba, Ajax, Ice Station Alpha, they were all great studies done on multi-year ice. In addition to that, I think other elements of MOSAiC that are different is the integration of models from the beginning. I mean, Shiba had a modeling component, but I don't think it was as tightly integrated as the modeling component for MOSAiC. The other thing that MOSAiC has, I mean, Shiba was basically an ice-ocean atmosphere experiment, where MOSAiC has those three elements and also adds ecosystems and biogeochemistry. And then there's, we have a lot of advantages in terms of improved technology. AUVs, UAVs, autonomous systems that will allow us to spread out a little bit more. So I think those are some of the differences. I think that there are some similarities. They're both year-long drifts, and I think they're both going to be, well, Shiba was challenging. I think MOSAiC will be challenging too, but MOSAiC is really an exciting opportunity, and it's, as I mentioned, it's a very big experiment.
Thanks. Ben Holt asks again a question related to those of Bill and Haley. Will the GPS buoy time and locations be available outside the ship during collections?
I'm not sure, Ben. But I can certainly check on that, or you could just email Jenny Hutchings. She's kind of one of the coordinators for the deformation array.
Thanks. William Manley asks, in regard to related data science, will you be adopting essential variables or otherwise standardized observations and metadata to improve interoperability of resulting data sets with YOPP and more broadly?
Yes, I believe that is the plan to make this data as easy to use as possible.
Thanks. Helen Wiggins asks, or she says, thanks, Don, great presentation and an exciting effort. Can you say a little bit more about how the programs will be funded?
Yeah, there's, as you might expect with 17 countries involved, there's a wide range of funding. I think each country has its own method for funding things. There have been a number of special calls in other countries about this. The Alfred Wegener Institute is certainly taking a leading role in coordinating this. For the U.S. component, NSF has been the primary funder of this, and it's been really exciting to see their participation. The Department of Energy is providing a mobile arm site, and so they're providing support in that way. And NASA is also providing support both in terms of remote sensing and supporting a couple of people on the ship to do ground truth.
Thank you. William Wong has a follow-up question. How soon will the data be distributed to the research community?
Again, I'm not quite sure about that because the data policy hasn't been finalized yet. The preliminary discussions has been like a year. The complete data set would be published a year or two after the completion of the experiment. There would be certainly data available to that, but I think that's still a topic of discussion.
Thank you. Stephanie Reinders asks, are there any wave measurements planned at the beginning or end of the cruise when the ship is in the marginalized zone?
I know as part of the distributed network there are some wave measuring buoys that will be deployed for the entire year.
Thank you. And Lauren asks, how deep will the ocean sampling go? CTD and gliders?
I don't know about the gliders. I know there's plans to do some very deep CTDs. I think there'll be more of a focus on the upper ocean, but I know there'll be some deep CTD cast. I'm not sure if they'll be weekly or bi-weekly.
Thank you. Ben Holt asks, regarding bottom surface roughness, it would be very interesting to collect this data from single MY and FY flows and over time with considerable detail. Does this match with what you mentioned?
Yes, that the plan is that we will have, again, in the idealized world where we find a wonderful flow to park against, and then we have young ice growing adjacent to it, that there'll be actually a few sites on the first year ice and a few sites on the multi-year ice where we'll routinely do terrestrial LiDAR.
Thanks. From Chensi Kuo, thank you for a wonderfully informative presentation. Where can we find out the specific instrumentation which will be deployed, acquisition schedules, and deployment sites? Thank you.
Yeah, in terms of the instrumentation, right now, the MOSAiC team is working on collecting a giant spreadsheet with everyone's instrument and sampling frequency, and whether or not it'll be in the central observatory, the distributed network. And that's scheduled to be completed by December. And I think once it's completed, it'll be put on the web.
Thank you. And from Leonid Yurganov, methane can be measured over the Arctic seas from satellites. Wintertime emission is detected. These data should be compared with direct sampling in real time.
Yeah, that's a great suggestion. Yeah, I think that definitely should be done.
Thank you. And from Lisa Mathis, in terms of outreach, will there be monthly updates about operations, teams involved, interested findings?
Yeah, I think one of the cross-cutting groups for MOSAiC is communication and outreach, because really, can you get more exciting than freezing a ship in the ice for a year? And I think that throughout the entire drift experiment, there will always be 2 public affairs officers on board the ship, one from Germany and one from the rest of the world to help coordinate things. And I think there'll be quite a bit of information going back and forth. I think also individual PIs all have plans to do outreach in their communities, and some work has started. Just yesterday, Matt Shoup sent out an email starting to coordinate the U.S. effort, so that we can kind of come up, share ideas on how best to portray MOSAiC in our community. So yes, there'll be quite a bit of outreach work.
Great. I don't see any other questions in the chat box. Encourage, we've got about 5 more minutes or 4 more minutes. So encourage people to enter questions if they've got them still. I see one coming in, I think. Meanwhile, is there anything that's come out of the questions, Don, that you'd like to follow up on?
Well, I think the main thing that I'd like to get across is this is just an incredible opportunity. If anybody has any additional questions, just send me an email or give me a call. By now, you probably have the sense that I love talking about MOSAiC, and I'm really looking forward to it.
There's one last question from Ben Holt. My last question was related to bottom surface roughness. That might be done with multi-beam sonar.
Yeah, and I think there's talk of putting that on one of the ROVs.
Great. And Sarah Chapman asks, is there a plan as to what science will be completed on the supply cruises?
Yeah, there isn't a finalized plan, but people have started making discussions. I mean, one thing that will be done is there'll be an ice watch, where as the ship traverses the ice cover, there'll be routine hourly measurements of ice conditions in terms of thickness, snow cover, pond fraction, whatever. There's also been talk of logging the met data along the cruise track. And I think there's, if you remember, those ships were coming from, there's a Russian icebreaker, there's the Odin from Sweden, there's the Zhulong from China, and I think each of those ships have some plans to do science in support of MOSAiC during those cruises. And again, that's something that's going to be discussed in detail at the March MOSAiC meeting that I mentioned.
Thank you. Nick Wayan writes, what weather and sea ice forecasts will the project be relying on? Thanks.
I think there's going to be a combination of forecasts that they get from shore, and then also some forecasts done on the ship. I think one of the things that will be really interesting is during the YOP special observing period, where there'll be this back and forth with observations going into YOP and forecasts coming onto the ship.
Great. And another question from Evelyn. Thank you for the clear and informative presentation. And Kabir Rasuli is also typing a question. Meanwhile, while people are still on, please stay on to complete the participant webinar or the participant questionnaire and evaluation as soon as we close. The last question is from Kabir. How detailed will the snow measurements be? Thanks.
Before answering it, I just want to thank everyone for listening in. It's been fun talking about MOSAiC. The snow measurements, the plan is to make them very detailed. Snow has been identified by the modeling community as an area where we really need to know more about it. Snow will be looked at in terms of, like on a large scale, what's the spatial distribution of snow depths? How does it relate to surface topography, whether there's a ridge or not? If a lead opens, how much snow gets blown into the lead and basically gets out of the system? How does, what's the temporal distribution of snowfall? There's also going to be a lot of effort looking at the details of the snow cover. There's been extensive planning on doing daily snow pits, again at different places where we expect the snow cover might be different, to look at the snow stratigraphy, to look at the density of the snow cover, and also one of the key questions is what's the thermal conductivity of the snowpack. So it's the planned snow measurements are really pretty extensive and pretty impressive.
Thank you. I think we'll go ahead and close. And on behalf of ARCIS and the SIP&2 leadership team, I want to thank Don Perovich for an amazing overview of the MOSAiC project. And I want to thank William Long for organizing today's event. Today's event will be archived and available online, and we will send notices to everyone that registered when those are available. Meanwhile, please do fill out this evaluation survey that you see on your screen now. This will help us in planning future events and in refining our webinar program. Thank you very much. Thank you very much for participating. Thank you, Don, for your presentation. And this concludes today's webinar.